Hello, my name is Auri. This is my 473 final project. Full disclosure, this isn't exactly what the final projects are intended to be based on the rubric or the assignment outline. I was going to spend all day today cramming out both the final presentation paper and the project, but then I got my grades back last night and realized that I have enough credit to pass the course already, and I'm in my 4th year and don't really care about my GPA at this point. But I'm still very proud of what I did, and I wanted to showcase it, so if you'll excuse the less formal and academic nature of this, I want to briefly go over what I accomplished this semester. So, my project was to make a volumetric fluid simulation inside of my Voxel game engine I've been working on for the past 6 years called Zepha. This is the engine. It already existed before the class. Obviously, it's been around for 6 years. And up until now, it's had the concepts of fluids, like in its memory representation, but it's never actually had a way to define or access or manipulate fluids. All content in this engine is defined in JavaScript files. There's effectively registries for each type of content, whether that be blocks or entities or fluids. And then they are processed using the V8 engine, which is a JavaScript runtime, which is used in Google Chrome. And then that data is fed into a native C++ application, which is responsible for the simulation and rendering. So effectively, for this assignment, I had to make a registry for fluids, which allows you to define fluids in JavaScript, which I can show if I go to this liquid file. So this liquid object is a registry. It has several utility methods like add, bind for events, emit events, get, remove, and unbind. And all of those functions trigger native C++ logic. So if I go to the Liquid Atlas interface, this is the interface that is exposed to the JavaScript API. It has a add function and a remove function. The other functions are handled automatically. They're effectively a template that's specialized. And the add function parses data out of the V8 JavaScript objects and into the native code. This is all C++ on this side. And what that does is it allows these liquid definitions in JavaScript for water and wine here to become part of the engine's registered content on the C++ side. The next thing that I did to actually make liquids creatable and usable is I altered a mod that I had already been creating called WorldEdit, which is mainly a bunch of developer utilities that allow me to quickly place blocks and manipulate the world. For example, if I want to set this entire region to stone. And I created a command to set and clear liquids. These commands are incredibly simple. They basically just go through the entire region that is selected, and if it does not contain a block that has collision, which right now effectively means that the block cannot hold liquid, then it sets liquid at that position with the maximum volume, which is currently 16. One of the goals that I had with this assignment was I wanted to create a system where liquids could exist at a more granular level than just a binary on or off for a specific block. So I wanted to be able to have multiple levels of volume for a specific block that would be represented by having different heights of the fluid in that position, which I did accomplish, which I can demonstrate really quickly by getting a transparent block here and giving myself a bucket, and as I right-click, you'll see that this layer of water, which is fairly primitively rendered, does raise every time I actually allow it to drop into this hole. This was accomplished by giving each block both a liquid type and a volume value, which are both encoded in a single U16, 4 bits of which are for the volume, which allows the maximum volume to go up to 16, because there's no concept of zero volume. That would just be the liquid type of empty. And then up to 4,096 distinct liquids that are stored in the engine at any given time, which I think strikes the balance between having a lot of flexibility in how many liquids can be defined and having enough data points for an individual block to, in the future, be able to have a much more advanced rendering engine that doesn't look as crap. So after I got the liquids loaded into the engine, I quickly made a render, and this render is very, very simple. It effectively just renders flat carpet-like layers of the liquid wherever it is set based on its volume. So if I quickly empty out this hole, and then I set the liquid here, you can see that it just looks like a plane, but if I kind of drop into it, you can see there's multiple continuous layers of the liquid in here. So each of these is full up on water. It is its maximum volume. And so effectively, each block that has liquid in it just renders a single plane with a height equal to its volume out of 16. And at that point, it was just static liquid. The next thing for me to do was to create a liquid propagation algorithm, which effectively, for me, meant that I needed to hook into logic when liquid is placed or destroyed or otherwise moved, add it to a queue of liquids that need to be updated, and then update them in a fixed time step. I didn't want it to be frame rate dependent. So what I did for that is when any method that is used to place or break liquids in the dimension atlas interface is called, so add liquid, remove liquid, clear liquid, set liquid, or get liquid. It calls the native function in the dimension, which I can go to here, which does a bunch of logic to actually handle manipulating the data, and then it also calls onChunkChange and liquids to process.insert. So chunk change is a function that is specialized by the world, which triggers a re-render of the terrain. So otherwise, we would not be able to actually see that liquid was added or removed from a position because it wouldn't cause a re-render of the chunk. This whole system is polygonal. It is not ray-traced. It uses greedy meshing and discrete chunks. So you can see kind of the chunk boundaries here by looking at these greedy mesh segments. And so when the chunk is changed, it re-renders that region, and then liquids to process takes in a position of any given liquid, and then when it gets called on a regular time step, it will actually propagate said liquids. That function, process liquids, is here. It clones the current set of liquids that need to be processed, clears the set, and then for each of the liquids in the set, it finds its type and volume, and then attempts to find an adjacent direction that either has the same type and a lower volume, or is empty. It scans every direction except for up, but it prioritizes down, so if there's a position straight down that liquid can fall to, then that is always done first. And then once it finds a right position, or a set of right positions, it chooses one randomly, and then moves the entire volume of the liquid there. That causes some odd behavior. For example, if I create a 2-block hole here, and I give myself a bucket, once again, and I place a level of water, you might expect when I place a second one that it would create 2 equally heighted liquid nodes, but instead it ends up effectively creating one that is twice the size, because one of the liquid nodes checks if it can move, and then it finds a second liquid node over to the side of the same type, merges with it, and then stops simulating. So that's a bit of a flaw in the system, and eventually I want to basically take all of the directions it can move, choose the amount it can move based on the volume of liquid in the current cell and the neighboring cell, and then evenly spread the liquid across the amounts that it can move in each direction, which should level a system over time. Another limitation of the system is that it only stops simulating when there is nowhere for the liquid to go. So for example, if I was to place a block here, you can see that it freezes the liquid here because there's nowhere else for it to move, and it stops simulating and stops updating properly. But as soon as I break a hole, and then I place another liquid node, I just crashed the game, or wait, no I didn't, sorry. As soon as I place another liquid node, it will start recomputing because it reactivates the blocks, right? And they never stabilize. In the future, I'd like to handle this by making it so that when liquids are at a minimum level, so effectively at 1 volume out of the 16 maximum, they will stop flowing unless they're affected by some velocity field that's defined by previous liquid movement, and then eventually evaporate. But for now, this system is effectively endless. It will never stop processing unless you force it to by either filling in the positions or clearing the liquid using world edit command. However, even with these limitations and relatively primitive flow mechanics of just choosing any random direction that it can move, I still get to have really interesting and compelling complex emergent behaviors from this. So for example, if I set this region to water, we're able to observe that it actually has a lot of characteristics of real volumetric water. Like, it flows down, and it will continue to flow across this field, a little more meandery than I would prefer. I'd like it if it was able to assess on a wider scale the gradient of the terrain and prioritize that, because right now, even though the liquids could be more granular, the blocks are not very granular. They are still either occupied or unoccupied, and so it's difficult when a node is, like here, for example, or I guess here is probably a better choice, to understand that this way is down and this way is up when all four potential positions are level. That said, it eventually does all end up flowing down, because by random chance, it will continue moving in directions, fall down one level of elevation, and then won't be able to rise back up. Which means that over time, the liquid simulation will continue, and it will fall all the way down from where we started up here to the basin below. And then promptly never settle, because I never programmed in settling. As far as optimization goes, I did not hit many of the performance metrics that I wanted to for this project. I had a lot of goals that I wanted to do with effectively analyzing the flow in and flow out of liquid within a fixed region that is larger than one block, and then, if stable for a certain period of time, actually freezing that node entirely, so liquids don't actually process on a block-by-block level in there, but they still continue to exude liquid on one side and consume it on the other, equal to the flow that was previously moving through it, which would effectively allow you to have constructs like rivers that come from a lake that is slowly draining and go to a lake very far away that's slowly filling, without having to actually process every node along the river along the way. Which is good, because the system currently is not particularly optimized for moving individual blocks of liquid. You can see on the right my task status graph, which is rapidly flashing. It's currently triggering a task to re-render every single chunk where a liquid has moved, which at this point doesn't have the granularity to only re-render the water, and actually re-renders all of the blocks in addition to the water, which is quite an expensive operation. And when I have a large amount of fluids, it tends to crunch quite hard. In the future, I want to separate that render pipeline so it only has to re-render the liquids as long as there isn't enough liquid to actually cause lighting or some other quality of the terrain to be altered. And then I might actually go a step further, and instead of generating the meshes on the client side at all, I might just use a mesh shader to generate the liquid mesh on the fly on the GPU. Because in the future, I don't actually want liquid to be represented as individual discrete planes. I'd prefer if it was a carpet mesh that ended up taking the volumes in the center of each block at any given position where there is fluid, and then evenly meshing a plane of surface water tiles over top of it, which would allow me to do nicer things like wave displacement and normal mapping, and generally make the water not look like it's individual little blobs of blue floating across the scene. Other than that, there's not really much else that I have done. It was a larger amount of work than I anticipated to actually get this entire system functioning. Despite the fact that there isn't that much code directly related to the animation of the liquids, managing more data in such a complex system as this, and then meshing it, and then displaying it, and then managing the update loop, was quite a lot of work. This is my largest project that I've ever undertaken, the entire engine project, to be clear. And it consists of over 70,000 lines of code, most of which are C++, and several of which I haven't touched in several years. And so it ends up being a large technical challenge every time I want to add a new significant feature to it. However, I found it really insightful to create such a system, because I was able to address a lot of different performance issues that had plagued the engine for a long time in order to make this as performant as it can be. It was exciting learning how to parallelize a lot of the logic here with meshing and displaying the actual liquid states and flows. It was interesting creating new APIs to manipulate the liquid, place it and remove it and define it. And it was also just exciting to see things happen, you know? It was exciting to create new functionality and then be able to see it in the world. There's something undeniably captivating about this strange game of life, Conway-esque simulation that's happening here just through each of these nodes randomly propagating. It might not be the behavior that I actually intended to have, but it is compelling behavior nonetheless. I also wanted to do other optimizations involving analyzing bodies of water and then allowing liquids to effectively get subsumed into a volume of significant size, such as an ocean or a lake, without actually having to recompute any of the nodes, and drain out of a volume of similarly significant size without draining the fluid volume itself, to try and simulate like the natural weather flow of evaporation and condensation. The idea being, if you start draining liquid from the ocean, you're never feasibly going to see the difference of that drainage, and so we shouldn't actually have to simulate that at all. But because I never ended up implementing world generation creating liquids, there was no realistic way for me to test and iterate on that. So that will be something that I work on in the future. This project, because it's not just a school project, is beneficial to me in a couple different ways. Mainly that I want to be able to continue having fluid dynamics in my engine, which I hope to eventually turn into a game that I release, and also because it allows me to do educational things like this in it, and have a framework for rendering already that is fairly sophisticated, that allows me to iterate on things like this in a way that would otherwise be prohibitively complicated to create from the ground up for the purpose of a school assignment. For a final segment of this presentation, I am going to stress test the system and effectively run it until it breaks here to give an idea of the performance metrics. I definitely did not hit the volume of liquid that I wanted to be able to simulate at once that I was hoping to, mainly because of the aforementioned issues with remeshing the entire chunk when I don't particularly need to. But those are all issues that I feel like I have a path forward into addressing, so I'm not particularly disappointed about that. This was mostly just a minimum viable, confirming that this system isn't a complete, like, insanity project level demonstration. So let's place a lot of liquid right here and see what happens. So the frame rate's definitely going to chug, but it should eventually stabilize a little bit, because at the very least, liquid simulation will stop when there's no potential places that it can move to, which will happen when there are multiple layers of water that exist on top of each other. The lower layers will stop simulating. One of the issues that I noticed with this propagation algorithm is that large bodies of water in height flow downwards a lot slower than they otherwise would have, because my set that stores the liquids that need to be propagated is unordered. And so a lot of the time, a liquid that is in the middle of a large volume that needs to move will try to simulate before the bottom layer, which needs to move downwards for anything to be able to have space, and then it will fail for that update step because it has no positions to move in. In the future, I would like to make it so that the set is ordered, and it will always simulate the lowest nodes of liquid before any higher ones, so that if liquid is falling down, the amount of liquid that's falling down doesn't matter, and it will flow down at a constant speed. Discussing how I want to move forward with this project is difficult because I have long-term goals that I want to address. I would like to have a more advanced meshing algorithm that can handle rendering the liquids entirely on the GPU, just with data points provided by the world, which can optimize the rendering of liquids propagating a lot more. I'd like to speed up the propagation step in general. I would like to use velocity fields for the previous directions that the liquids went to bias their movement, especially on shallow terrain differences, like the ones that we discussed earlier, where there might be multiple blocks before an elevation change, to allow liquids to continue moving if they're going down a shallow slope, as opposed to just stopping and stagnating. Looks like I hit a performance boundary, yep. Okay, perfect. And then finally, I would like to be able to handle multiple liquids at once, which have different interactions. Right now, you can define more liquids at once, but they effectively stop simulating once they end up interacting with each other, which I can demonstrate. If I quickly create myself a hole, and then I create a wall in between, and then I create some water over here, and then I create some wine over here, the two liquids which are currently defined. And then I proceed to break this wall. You'll see that they mix into each other, and it looks kind of satisfying, but then they eventually effectively freeze. Everything other than the top layer, which is still re-updating because we don't have any sort of system that levels out liquid within the span of one block, ends up freezing down below wherever it stopped moving because it was surrounded by other liquids. It would be nice to be able to have an API-defined collision event with other liquids. So for example, Minecraft-like behavior where water collides with lava and turns into cobblestone could be employed. But yeah, this is mostly the project that I created. I don't have any other details to present. I had less time to work on this than I hoped due to a lot of work. This is my first semester managing a full-time job, and also trying to spin off a full game that I'm hoping to create into a commercial product eventually. And there was just a lot of other life hassles that got in the way, but I had a lot of fun in this course, and I really enjoyed creating what I did create. I understand that academically this isn't the most successful project as that is likely to be seen in this course, but that wasn't a particular concern for me. It was mostly that I wanted to get interesting information out of this course and be able to complete my degree, which I think I've accomplished both of. So yeah, thank you for taking the time to listen to my mostly unscripted ramblings and look at my project. I appreciate if this video actually gets published, and I hope that I made something interesting and compelling for people to see. Thank you very much.